All right, the ratio test. This one's awesome because it's plug and chug and because it works like a lot of the time. So it sort of makes a lot of the tests we've looked at so far pointless or redundant or annoying because it works so much of the time that you're better off just plugging and chugging through the ratio test and seeing what happens. Other times that this definitely works at best are if you have an n factorial. Factorial is when you have the exclamation point. So that'd be like, you know, I'll show you how to deal with those. We're going to get really good at canceling factorials. But the moral of the story is, all you do is you make a limit problem. Limit as n approaches infinity, just like we did with the limit comparison test. But then instead of comparing your sequence or your series to a different series and having to come up with a good one to compare it to and all that kind of annoying stuff, instead, all we're going to do is compare one term of our series to a different term of our series. We're going to compare the n plus 1th term to the nth term, and I'll show you how that works. It's really simple. We're literally just going to plug in n plus 1 to the formula for the numerator and plug in n for the denominator. And that's going to make a ton of stuff cancel out. And then as usual, we'll get an answer which is r, and then there's some values we like, some values we don't like. When you take this limit problem, if r is less than 1, that means the absolute value is less than 1 because it might be like a negative 1/2, then the series converges. If r is greater than 1, it diverges. And if r equals 1, that's unfortunately indeterminate. So in that case, the ratio test doesn't tell us if it converges or diverges. We'll have to come up with something else. But a lot of the times, especially for really complicated series formulas that have n factorials and n exponents and all that kind of stuff, this is really going to work great and very quickly give us an answer. All right, so to give you an example, here's one with an n factorial in it. It's likely this thing converges, right? Because it looks like as n approaches infinity, the terms get smaller, very small, and approach 0. So decent chance it converges. Let's take a look. So all we have to do is take the limit as n approaches infinity of a sub n plus 1 over a sub n. So we're going to take the limit as n approaches infinity. So all we have to do is plug in n plus 1 to the formula. So our numerator is just 1 over n plus 1 factorial. And then the denominator is just a sub n, which is just the formula we were given. All right, so to simplify this, I'll just start over down here. This is always going to happen with the ratio test, is you'll have a fraction divided by a fraction. So you just invert and multiply, to that second one. So we have n plus 1 factorial times, and then invert and multiply, and we just end up with a, oops, not n squared, n factorial over 1. So we've got the limit. I'm doing a bunch of steps here that you'll probably skip once you get good at these. I just want to show you very clearly what's involved. All right, so at this point, we've got n factorial over n plus 1 factorial, and we're probably thinking, uh-oh, Chris, I don't know what to do about that. Because this is actually kind of wacky, right? If it was just n over n plus 1, the limit would be 1. If it was just n over n plus 1, because the 1 would be insignificant, do L'Hopital's, whatever, however you look at it, the limit of n over n plus 1 without the factorials is just 1. But we have the factorials, and it turns out that makes a really big difference. So we've got to figure out a way to reduce this algebraically. It turns out the big trick here is to recognize something. N plus 1 factorial. So n factorial, you know how if you had like 4 factorial, that would be 4 times 3 times 2 times 1. You're basically taking the first number, then you're multiplying by 1 less, then 2 less, then 3 less. You just reduce by 1 each time, right? So another way of writing n factorial would be n times n minus 1 times n minus 2 times n minus 3. You just keep doing that all the way down to 1, right? So what does that mean n plus 1 factorial would be? Well, the first number is just n plus 1. And then the next number is going to be n plus 1, 1 less than that. But 1 less than n plus 1 is just n. And then 2 less than n plus 1, 1 less than n is n minus 1. And then 1 less than that is n minus 2. So you can see that n plus 1 factorial and n factorial have every term in common except that n plus 1 factorial has an extra n plus 1 on the front. And that's the key in the ratio test. So I'm going to rewrite this. I'm just going to leave the top n factorial. And I got to rewrite n plus 1 factorial as n plus 1 times n factorial. Because remember, when I do n plus 1 factorial, it's just an n factorial with an extra n plus 1 on the front. And once you write it like this, you're like, well, hey, wait a minute. N factorial and n factorial just cancel out. So I basically just got 1 over n plus 1. So what is the limit as n approaches infinity of 1 over n plus 1? It's 0, right? Because 1 over infinity is 0. So, and remember, this was all r. Like when you're doing the ratio test, what you're, that ratio or whatever, what you're solving for, that number you eventually get, that's your r. So the question is r bigger than 1 or smaller than 1? Well, it's smaller than 1, so this converges. And that's all there is to it. So it turned out it was a really simple problem to set up. The trick was this factorial nonsense, but the factorial nonsense gets really easy once you've done a few, and these are actually really fun because, let's face it, canceling stuff is fun. So you actually look forward to seeing factorials because that kind of takes the guesswork out of it. You're like, if you see a factorial in a series problem, you probably want to use the ratio test. So let's do another one. Remember, I don't have to think, I just have to plug and chug. So I'm just going to do a sub n plus 1 over a sub n. So that's going to be, when I plug in n plus 1, I get e to the n plus 1 over n plus 1 factorial divided by e to the n times n factorial. All right, so when I invert, and of course there's a limit as n approaches infinity on that, so I'll just write down here so I can keep everything a little bit neater. All right, so I'm just going to, I keep the numerator the same, then I'm going to invert and multiply, to divide fractions. So I got e to the n plus 1 over n plus 1 factorial times, invert and multiply, I got n factorial over e to the n. All right, so you're probably seeing that we've got that factorial trick again to take care of. So it's pretty obvious that this n plus 1 factorial, I'm going to want to turn that into an n plus 1 times an n factorial, because that's going to help me cancel this n factorial up here. So this n factorial here, boom, boom, awesome. Did some good work there. What about this e to the n though? So I got an e to the n down here, and I've got an e to the n plus 1 up here. How am I going to cancel those? Well, it turns out this is kind of a subtle trick, but if I had x to the 5th over x to the 4th, wouldn't that just reduce to x? If I had e to the 6th over e to the 5th, that just reduces to e because the exponents are off by 1, so I just leave an e to the 1st where the bigger one was. And that's what's going on here. I don't have numbers. So like, unlike 5 minus 4, which is 1, or 6 minus 5 is 1, n plus 1 and n, it's not super obvious that those cancel, except isn't n plus 1 just 1 bigger than n? So it's exactly like what would happen if I had e to the 6th over e to the 5th, or e to the 15th over e to the 14th. There's a difference of 1 there. So I can cancel this with all this and just leave the 1. So essentially just leave the e. And that's what I'm going to do. So again, right here, cancel that with this whole thing, and I've just got an e upstairs. So it turns out this whole thing has reduced. The n factorial is gone, so I just have an e, and I have an n plus 1. So what's the limit of this? Well, e, since e doesn't have an exponent anymore, like of n or something, e is just a constant. It's 2.7. It's nothing. So if the denominator is approaching infinity, and the numerator is just a constant of 2.7, this limit of a small number divided by infinity is going to be 0. So that means r equals 0. Remember, that's my r that I just found. So that number I get at the end, if that's less than 1, the series converges, and therefore this series converges. All right, let's do the ratio test on a p-series. Now I'm only doing this to sort of show you that where the p-series test comes from. And this might seem kind of circular because I'm using a p-series to verify the ratio test, but then I could use a ratio test to prove the p-series test. It's kind of like all these theorems prove each other, and unfortunately that's how it goes, but at least they're self-consistent, internally consistent. So let's just apply the ratio test. Now I'm expecting this to converge, right? Because it's a p-series, I have n to a constant exponent, and that exponent is bigger than 1, so I'm expecting this thing to converge. So I've got 1 over n plus 1 squared over 1 over n squared. So if you invert and multiply, you get n squared over n plus 1 squared. And interestingly, oh, wait a minute. All right, so if I FOIL this out, I've got n squared over n squared plus 2n plus 1. What's the problem there? Well, no matter how you look at this, do L'Hopital's whatever, this limit equals 1. So is that a problem? Yeah, it's a problem because the ratio test, if it's bigger than 1, that's great, it diverges. If it's less than 1, it converges. But if it equals 1, it's indeterminate. So basically the ratio test, the one time it doesn't work is when the ratio ends up being 1. And it turns out that for any p-series we test, that's going to be true. So we got an indeterminate answer on something we know converges. But similarly, if we wanted to test the harmonic series, which we know diverges, 1 over n, if we want to see if that diverges, once again, if we do the ratio test, we're going to get 1 over n plus 1 over 1 over n. Invert and multiply, we get n over n plus 1. Limit as n approaches infinity, obviously. So the limit as n approaches infinity of n over n plus 1 is also indeterminate. By L'Hopital's whatever, well, the limit's 1. But the point is that's an indeterminate ratio test. Because when you get 1 as your answer to the ratio test, that's indeterminate. So it turns out that there's some series the ratio test doesn't work on, but luckily it's ones that are already really easy to do with other tests, like the p-series test. So if you don't notice something's a p-series right away, and you're sort of using the ratio test for everything, because why not? Because it's easy. And you get an equals 1, very often, the times you get 1 out of your ratio test are times you can very easily solve the problem without even doing any math. So right when you walk up to this, you should be like, oh, that's a p-series with p equals 2. That converges. This is a harmonic series, or a p-series with p equals 1. Point is, it diverges. So without even doing the ratio test, we could have solved these faster than ratio test. And the ratio test is already pretty fast. All right, 1 over n to the n. This is one that we earlier tried to use the conversion test on. Comparison test. And it turned out you can compare this to almost anything and it would converge. Well, guess what? It works for the ratio test too. So we'll take the limit as n approaches infinity of 1 over n plus 1, the n plus 1, over 1 over n to the n. So you invert multiply and you get the limit as n approaches infinity of n plus 1, invert multiply, so n to the n is upstairs, and n plus 1 to n plus 1 is downstairs. All right, so basically, this one's sort of hard to do with L'Hopital's or anything like that. Although if you did L'Hopital's on it, if you FOILed out the bottom, and we can't actually FOIL it out because we don't know what the exponent is, it's just n plus 1, right? But if you FOILed out the bottom, not n plus 1, limit as n approaches infinity. So the top is just n to the n. If you FOILed out the bottom, you get a lot of terms of various exponents, but the highest term you would have is n to the n plus 1. That would sort of be the highest power term of the polynomial, and everything else is going to have some n's to the n and n to the n minus 1. We'll have every power of n, but the biggest one is the only one that matters for limits, right? And you can see that if you took L'Hopital's, all this other stuff would just kind of gradually drop out, and what you would be left with, your final step of L'Hopital's would be limit as n approaches infinity of 1 over n. Because basically, whenever you're taking a limit as n approaches infinity, if the power downstairs is bigger than the power upstairs, it approaches 0. So this thing approaches 0, and the ratio test gives us something that converges. Kind of feel bad that we haven't shown anything diverges with a ratio test, but the same thing would apply. I mean, let's say we wanted to take the sum of, I don't know, n factorial. Does that converge or diverge? Well, let's try doing it. So we take the limit as n approaches infinity of n plus 1 factorial over n factorial, which is going to be the limit as n approaches infinity of n plus 1, because when factorials, you always want to take that to an n plus 1 times an n factorial. N factorial, those cancel. And we get the limit as n approaches infinity of n plus 1, so obviously that's infinity. And infinity is bigger than 1, therefore this diverges. But again, that's one you could have easily gotten by just, this doesn't even satisfy the nth term test. Remember, for anything to converge, for the series or the sum to converge, the terms have to get tinier and tinier and approach 0. But if your terms are n factorial, they get really big really fast. So this is not something that ever had, a ghost chance of converging anyway. If we had n and we've done others anyway. So the point is, ratio tests, pretty easy to use, especially if factorials are involved, and sometimes they will diverge. But it seems like when you're using a ratio test problem, you either get 1 or it converges. All right, last one we'll do in the ratio test. Just looking at this one, I've got a slightly bad feeling, because the ratio test, the things that it really works great for are the things we've seen. Anything with n factorial in them, we've seen how n factorial and n plus 1 factorial cancel out really great and leave an n plus 1 behind, so those are nice. And we've also seen that things raised to a power of n cancel really nice. So earlier we had an e to the n that canceled with the e to the n plus 1 that ended up being in the numerator. If you had 2 to the n, similarly you'd also have a 2 to the n plus 1 that would cancel out really nicely. But I'm not seeing either of those in this one. So sort of the classic tip-offs that you should be trying the ratio test are not present. And by the way, some of the stuff I just listed up here, like for example this stuff, that's all typical of geometric series. So if you spot that something's a geometric series because it has these in it, then you might just right away go to the geometric series test, except, as usual, things can be off. Like, let's say we had n equals 1 to infinity of n factorial, like e to the n over 2 to the n plus 1 or something, where it's not super obvious that you can convert it to a straight up geometric series. So this would be a good candidate for the ratio test. This one, however, does not have any of those telling signs that it should be used. I should use a ratio test, but let's try it anyway and see what happens. So we'll take the limit as n approaches infinity. All right, so we want ln of n plus 1 over n plus 1. That's my a to the n plus 1 term. And then downstairs I've got ln of n over n. All right, so if I just invert and multiply, of the ln, ln n plus 1 over n plus 1 times invert and multiply the bottom one, we get n over ln of n. All right, now it's not super obvious what this limit is. I'm going to say it's 1 though. And I'll give you a logical reason to explain that. Most teachers won't make you do this. I mean, technically you could probably do L'Hopital's on this, and it would be a product rule for both top and bottom because you have n times ln n plus 1. But if you rearrange this, just switch the top and you'll get, if I just switch the order of n, so I get n times ln n plus 1, that's just the same numerator I've got. I just switched the order of multiplication. And I did that so it could do, and leave the bottom the same way it is. And now you'll kind of see, we really have, it's like two fractions multiplied together. The limit of this is obviously 1 because, just n over n plus 1, as n gets big, the 1 doesn't matter anymore, just have n over n, which is 1. And then same problem here. N plus 1 and n are basically the same when you get to really big values of n. So the natural log of two equal numbers is equal, so this is also going to be 1. And 1 times 1 is 1. So the limit of this mess is 1, which for the ratio test is bad, right? Because 1 is indeterminate. It did not give us an answer. And that sort of confirms what we already thought, which is, oh, hey, man, this doesn't have either the telltale signs of a good ratio test problem, either an exponent of n or a factorial. So it turns out that we needed to use a different method for this one, and the comparison test is the most obvious thing to do because it really looks like a harmonic series. So if we compare it to the harmonic series, it becomes a pretty straightforward comparison. It's not super straightforward, but I'll show you that the terms of harmonic will be 1 over 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And then the terms of this series are going to be ln of 1, which is 0, and then ln of 2 over 2, plus ln of 3 over 3, plus ln of 4 over 4, dot, dot, dot. So for the comparison test, I suspect this thing diverges, right? I'm comparing it to a divergent series, a harmonic series. So I need to show that each term of my series is bigger than the corresponding term of the harmonic series. And that actually is true for most of these terms, but not the beginning. At the beginning, you can see the harmonic series is bigger than my series, because 1 is bigger than 0. And 1/2 is actually also bigger than ln of 2 over 2, because ln of 2 is a decimal. It's like 0.9 or 0.8 something. So this term, 1/2 is actually bigger than this, and that's opposite. I want my series to be bigger than the harmonic series, bigger than the divergent series. But if we ignore these first two terms, as we're allowed to do for the comparison test, beyond that point, my terms are all bigger than the harmonic series. ln of 3 is 1 point something, and 1 point something over 3 is bigger than 1 over 3. So this is a successful comparison. ln of 4, I don't know what it is off the top of my head, but I know it's bigger than 1. And so ln of 4 over 4 is going to be bigger than 1 over 4. So again, my term wins, and that's going to happen indefinitely. So once we're past those first couple of terms, my terms are always bigger than the corresponding harmonic series term, and therefore the comparison test gives a pretty straightforward divergence. So the ratio test, really great when you see elements of things that you could have worked out without the ratio test. But when they're put together, like if you have an n factorial and a 2 to the n, and then maybe in the numerator there's an e to the n, and you just have a big mess, that's when the ratio test really shines, is when you have very complicated looking tons of junk. It's like the more junk, the more n factorials, the more sort of separate elements they put in the n formula, the bigger and nastier this formula gets, the more likely that you're going to want to use the ratio test. It'll just be a bunch of fun algebra because we love canceling, so that's why the ratio test is for you. And then the ratio test also works really great on geometric series, which if you don't spot them, the ratio test will do it for you. So again, this is something students really like, it seems like. And when in doubt, try the ratio test. What the heck? And even if it doesn't work, if you get a 1, you still might get a little bit of insight into like, oh hey, that kind of looks a little bit like the harmonic series. Maybe I should just do a comparison test on that.